so maybe I'll get started. And so we'll go in the order in which talks appear in the proceedings. And I think, okay, Paul is giving the talk, not me. Okay, so yeah, so sorry about the errors. Yeah, so neither of you responded to the emails. I wasn't sure who was talk. Okay, yeah. So anyway, so yeah, so we have 5 talks in this session, and each will be for about 10 minutes. And so the talks, we'll do them in the order that they appear in the schedule. The first talk will be on sublinear time and space algorithms for correlation clustering, and Wang from Rutgers will speak about this work. And then we have this talk about sparse Boolean factorizations of matrices. This is by Ruizhe, Zhang, and this is with joint work with like Sitan, Chen, Zhao, Song, and a bunch of others. And the next 2 talks will be somewhat related, I think, from what I can tell. And so yeah, one is multivalid learning, and that will be given by Georgy Novarov. And we have Omni Predictors, talk by Parikshit, who's the nice introductory slide as we saw. Okay, and the final talk will be given by Paul, and it will be on Sub-Gaussian mean estimation in very high dimensions. Okay, so yeah, so without further ado, maybe we can get started. And so we should at this, I mean, if we stick to about 10 minutes per talk, we should have some time for maybe a question after every talk. So I'll be monitoring the chat, and so just for the speakers, I might just like raise my hand if I see some questions in the chat. But we won't interrupt you during the talk. So unless it's something super urgent, so we'll just wait till the end of the talk. Okay. So hope that makes sense. So that said, yeah, so let's welcome the first speaker, Chen Wang of Rutgers.
Okay. Yeah, I can stop sharing. Okay. Can share. Good. So you can see my screen, right? So it doesn't. Good. Okay, then let's get started. So hi everyone. Today I'll be talking about our recent results on sublinear time and space algorithm for correlation clustering. And this is a joint work with my advisor Sepehr at Rutgers. So to begin with, let me motivate the problem and give you the definitions. So this is a machine learning problem. So it has like real world applications. So suppose you're given n documents, okay, like these documents. And these documents are either similar or dissimilar. Think about each pair of them of some topics. For example, I have these 3 documents, first about US election, second about UEFA Champions League, and third about climate change summit. The goal is to find a clustering that puts similar documents together and dissimilar ones apart. Okay, for example, among these 3 documents, you're going to put the first and third together. They are similar, more or less about politics. Second one is about sports, so they stand alone, put them in a separate cluster. Okay. So formally, in correlation clustering, we are usually giving a labeled graph G. So as convention, V as set of vertices and E as set of edges. So in fact, we are dealing with a complete graph. That means for each pair of vertices, there's an edge. And each edge is labeled as either negative or positive. Okay, for example, if I give you this graph, it has 5 vertices. There's a positive edge with 1v2, negative edge with 1v3, 1v4, and so on and so forth. So usually we are interested in minimizing this disagreement cost. So what does it mean? So suppose we are implementing the clustering as shown in the picture, but there are 2 types of edges we are going to charge costs. The first one is positive edges across different clusters. For example, this V2, V4. You can think of they are similar documents, but in the different clusters. The second one is this negative edges inside the same cluster. For example, this V3, V4. You can think them as the dissimilar documents, but in the same cluster. Okay. So more formally, we are just going to enumerate all of such pairs that they share a positive edge, but in different clusters, plus this share a negative edge, but in the same clusters. Sum them up, count them, and then this is the total disagreement cost. And our goal is to minimize the total disagreement cost. Okay. So let me tell you some about state of the affair and our contributions. So there are some classical results about this correlation clustering. We know the exact solution is NP hard. So the best polynomial time approximation gives a 2.06 approximation with some linear programming techniques. So there is a combinatorial algorithm called pivot algorithm achieves 3 approximation. Okay. But polynomial time algorithm is not the end of the story because in more than massive data applications, so sometimes even storing or reading the entire input itself is prohibitively expensive. So we need to deal with these like sublinear algorithms, which works with resources substantially smaller than even the inputs themselves. Okay. So there's a quest for sublinear algorithm for correlation clustering. So we studied both the sublinear time and space algorithms. So for the sublinear time regime, before our work's best known result is this local correlation clustering algorithm by Baumchi et al., which they show that you can achieve like 3 opt plus epsilon square approximation in order of n over epsilon square time, given the adjacencies. Okay. So there is an epsilon n square additive error, and this seems inherent because they also prove a lower bound, saying that if you're only allowed small n square time, there exists this small constant Cn epsilon such that we cannot do better than C opt plus epsilon square. Okay, so we need a new model if we want sublinear time for purely multiplicative approximation, and we use this positive subgraph G plus in our work. So our first result basically settles this problem. So we show that there exists a sublinear time algorithm, finds the constant approximation for correlation clustering with high probability in order of n log squared time. Okay, if given the positive subgraph adjacencies. This is almost a quadratic improvement. And we also studied sublinear space correlation clustering. So we studied this with the graph streaming models. Under this model, the vertices are given in the beginning, edges arrive one to another in a stream. So for example, if you have 5 vertices, in the beginning, there are only vertices. T equals 1 is positive edge before V5 arrives. T equals 2 the negative edge V1, V4 arrives, and so on and so forth. Okay, so a streaming algorithm ideally only works with a single pass, and it's interesting when its memory is smaller than the worst case input size. And the dreamland scenario is this semi-streaming memory, order of n polylog n. So also notice the O tilde n, so which is usually the memory necessary to output the answers themselves. There are some algorithms that achieves constant approximation with O tilde of n memory before, but all of them requires more than one pass. And before our work, there's no known algorithm with more than with a single pass that achieves constant approximation. So our second contribution is basically to settle these problems. We give a single pass streaming algorithm with high probability find a constant approximation for correlation clustering with the order of n log n edge space. Okay, this is almost optimal. So the next 4 or 5 minutes, I'm going to talk on the high level our algorithm in a nutshell. So the earlier sublinear algorithms usually simulate the pivot algorithm, which is very elegant, and it essentially computes a maximal independent set on the positive subgraph. However, there's a quadratic barrier if you want to compute it in sublinear time, given the adjacencies or over a single path of the stream. Okay. So very recently, this elegant work by Cohen and Aditya achieves the constant approximation in 6 passes, but didn't use the pivot idea. So I won't dive into their algorithm, but if you trust me, if I give you a graph like something like this, it has some densely connected components and some rather standalone vertices. So they will put these densely connected components in the same clusters and standalone vertices apart. So in other words, their algorithm implicitly, they didn't do a decomposition, but they implicitly divides the graph into densely connected components and vertices with sparse edge connections. So we observe that this kind of decomposition is not first of its kind. So there exists this graph sparse-dense decomposition, first studied in the graph theory literature, and more recently in the distributed and streaming graph coloring. So what does it do? So roughly speaking, it partitions the vertices into 2 classes, almost cliques and sparse vertices. So almost cliques are the vertices that densely connected with each other and their degrees are high. So for, let's say, like around the maximum degree delta. And for vertices that cannot join any almost clique, they are sparse vertices. So for example, if I give you this graph, I will mark the red vertices as almost cliques because they are densely connected with each other and their degrees are high. And the light blue vertices as the sparse vertices. Okay. And now we can just do correlation clustering by this strategy. We can decompose on the positive subgraph G plus and put for each almost clique, we put in a separate cluster, and for each sparse vertex, we put as a singleton. So we have this kind of strategy. And for example, on the graph I showed you before, we will just place the clustering as shown in the picture. Okay, so we have this kind of, we give a graph, we find the sparse-dense decomposition, and do Gaussian clustering. But now this is not the end of the story because there are some problem with the canonical graph sparse-dense decomposition. The first problem is only works on with the maximum degree delta. But this creates a problem because if you look at the graph as this is a 3-click, but it will, because its degrees are low, they will like decompose as sparse vertices and use a lot of costs. So there exists a version of local graph sparse-dense decomposition by Alon and Assadi, which admits a local version of decomposition, which means for this like local click, it will also recognize as almost click. But there are several problems to just use their paper, and one of the problems is that their work emphasizes on the existence of such decomposition, and it's not clear if there are sublinear time and space algorithms to find them. So in this work, we basically like design a new decomposition that requires order of n log n such samples with high probability, and we can find the decomposition in order of n log squared time. And we further prove that these samples can be obtained in order of n log n time with the positive agency limits, or order of n log n edge space over a single parser string. Okay, so in a nutshell, we basically did this, and now we can collect the samples in sublinear time or space under the respective model, run in order of n log squared in time, and find the decomposition, and do the clustering in order of n time and space. Okay, and that's basically our algorithm. There are some open problems. The first problem is right now our approximation factor is constant, but it's large. It's 10 to the 5th to 10 to the 6th. So if we want to like reduce the constant, so what can we do? And is there a lower bound? And we believe that our algorithm works much better than the worst case guarantee in real world applications. We can test empirical performance. And the final thing is that, so another interesting problem is to test the optimal value for cohesion clustering without output the clustering itself in very small space, let's say polylog. So for more detail, please check our longer talk, and thank you for your attention.
Thanks a lot, Chen. This is a very good talk and right on time. So, does anyone have like quick questions for Chen while I think Ruizhe sets up? So it's not. I mean, I just had one very quick question. Like your algorithm, does it use only like a single pass through the data, or does the sampling and these other steps do you require different passes for them?
No. You can do
I
like
think it's just single pass.
yeah,
All of them.
sampler, but not that easy. Like it's doable. It needs some like modification for the reservoir sampler. Yeah.
All right. Yeah. Thanks. Okay. So if you can stop sharing, I think Ruiz can share.
Thank you.
All right, great. Yeah, we see your slide. So the next talk is given by Ruizhe Zhang from UT Austin. He's talking about sparse Boolean matrix factorization and some of the application. So go ahead.
Okay. Hello, everyone. I'm going to talk about symmetric sparse Boolean matrix factorization. It's a joint work with Sitan, Chen, Zhao, and Runzhou Tao. So let's get started from an old problem. It's called non-negative matrix factorization. Here's the definition of NMF. So you are given an n by m matrix M and also a rank parameter R. You are asked to find an n by R non-negative matrix W1 and M by R non-negative matrix W2 such that their product W1 times W2 transpose and M's the distance is minimized. So for this old problem, it has many different applications in many different areas. More recently, there are some variants of the NMF problem. So the first kind of the variant is called the symmetric NMF, which requires the two factors W1 and W2 are equal. For this problem, it's related to the kernel k-means and also related to the graph clustering problem. Another variant of NMF is called the binary value NMF, where in this setting, the W1 and W2 can only take values in some binary set like 0 or 1 or plus minus 1. For binary value NMF, it has some applications in coding theory and also in like graph partition and Boolean factor analysis. A third variant of NMF is called the sparse NMF, where the W1 and W2 are required to be some sparse matrices. And in this work, we consider the NMF problem with all of these three kind of additional constraints, which is the sparse symmetric Boolean matrix factorization, or denoted as SSBMF problem. So here's the more formal definition of SSBMF. So you are giving a symmetric matrix M in the with dimension M by M, and also two parameters K and R. So you are asked to find M by R Boolean matrix W such that each row of W has exactly K ones, and you are asked to minimize the number of different entries between M and WW transpose. We discovered that this problem turns out to have many natural motivations from theoretical computer science and machine learning. The first motivation is about clique decomposition. So if we regard the given matrix M as the adjacency matrix of a graph G, then the factor W will encode a clique cover of G, which partitions the edges of the graph into several cliques. And the sparsity constraint becomes the constraint that each vertex of the graph belongs to exactly K cliques. And this is an example. So this problem also helpful in analyzing the social network. And another motivation comes from the combinatorics. So if we regard the factor matrix W as an incidence matrix of a K uniform hypergraph, here the K uniform hypergraph means each hyperedge contains exactly K vertices. And then the given input matrix M is the adjacency matrix of the line graph of H, where each hyperedge corresponds to one vertex in the line graph of the hypergraph, and the two hyperedges are connected in the line graph if and only if these hyperedges overlap in the hypergraph. In this setting, the SSBMF problem just asks for reconstructing the original hypergraph, giving its line graph. And this is also an old problem in combinatorics. When K equals to 2, which corresponds to the graph case, this problem is easy, and we already have many nearly linear time algorithms to solve the line graph reconstruction problem. However, when K is large, this problem turns out to be NP hard, and it also implies the worst case hardness of SSBMF problem. Basically, if you assume P not equal to NP, then you cannot hope to exactly solve the SSBMF problem in polynomial time. And the third motivation comes from the security of machine learning. So InstaHide is a recently proposed scheme for privacy training neural networks on images. Roughly speaking, it constructs each synthetic public training image using random linear combinations of K private images. And the security of InstaHide is an important problem, and some attacks on this scheme has been proposed. And we observe that a case step of these attacks can be exactly formulated as an SSBMF problem. And it implies that this attacking algorithm implies the average case algorithm for SSBMF. Why these are average case? Because each synthetic image is generated from a random linear combination of K private images. However, these algorithms are either heuristic or only work for certain parameters, and we hope to obtain a more general and provable average case algorithm for SSBMF. And this is our first main result. We propose an average case algorithm for SSBMF. So let me first state the distribution assumption of our algorithm. So we assume that each row of the ground truth W is an independent uniformly random K sparse Boolean vector, and the given input M just equals to W times W transpose. Here W is the ground truth. And the matrix multiplication is over the Boolean semi-ring. Then we prove that as long as M is large enough, we can efficiently and exactly recover the factor matrix W up to a permutation. And the running time is just M to the omega plus 1. Here, omega is the matrix multiplication exponent. As a corollary, our average case SSBMF algorithm can be used to solve the so-called batch k-vector sum problem. So this problem is a generalization of the famous k-sum problem, and it's also a mathematical abstraction of the inside attacking. So as you can see, the famous k-sum problem is a special case of this BKV sum problem with the dimension d equals to 1 and the public vector m also equals to 1. And we prove that under some distribution assumptions, we can recover the heavy coordinates of each hidden vectors x1 to xr very efficiently. And also in our paper, we prove a worst case guarantee for the SSBMF. Although in the worst case, the exact working of SSBMF is NP hard. For an epsilon approximate working of SSBMF, we give a quasi-polynomial time algorithm. We use a 2CSP solver to get this worst case algorithm. So now let me talk about a few open questions about sparse symmetric Boolean matrix factorization. The first open question is about the worst case approximated SSBMF. So can we improve our algorithm that's based on 2CSP solver? So for example, can we give a fixed primary choice tractable algorithm, which runs in time polynomial in M, but some functions in other parameters? Or can we rule out this possibility by proving the hardness of approximation for SSBMF in the worst case? And the second open question is about the batch k-vector sum problem. In our paper, we discovered that it has some applications in machine learning security. Can we find more cryptographic applications of batch k-vector sum? And also, can we prove the average case hardness of batch k-vector sum problem? That's all. Thank you.
Thanks a lot, Ruizhe. It's a great talk, and thanks for sticking to the time as well. So any questions for Ruizhe? While maybe you can stop sharing, maybe Georgie can start setting up, but meanwhile, any questions? About your open questions, like, do you, like, for all you know, additive approximation could be possible efficiently, right? Or can you rule that out also from your hardness result?
No, we even for the additive approximation, we only have a quasi-polynomial time, but we cannot get a purely polynomial time algorithm. But we can also, we currently do not know how to prove the hardness of even for the additive approximation.
Yeah. All right. So yeah. So if there are any other questions, feel free to keep typing the. Yeah, one thing I forgot to mention is that for those of you who are in the audience, you can feel free to type questions for any of the speakers. So some of them have agreed to hang around after the session, so they might answer after we are done. Okay, so feel free to do that. And so let's go ahead and start the next talk. So this is online multivalid learning, and the speaker is Georgie Noorov from UPenn. Go ahead.
Thanks. Yeah, this is joint work with a bunch of awesome people at UPenn and Ruizhe. Varun Gupta, Zhang, and one of my advisors, Aaron Roth. And just at a glance, basically what we do is we obtain uncertainty guarantees that are with respect to a potentially large collection of subspaces of the sample space. So you can think of it as predicting something about individuals, and we want to be confident when predicting something about them on all these specified subpopulation groups, essentially. And our technique is interesting in its own right. It's a simple and general game theoretic tool, and hopefully we'll go over it briefly. Okay, so first of all, why should we care about uncertainty guarantees? Well, traditionally, of course, building and training accurate models has been the predominant line of research in machine learning. But of course, it is very important that these models are also confident in what they're predicting. And of course, conditional guarantees would be the strongest type of guarantees. So imagine for a certain individual X, predicting a prediction interval just for that individual. So the probability that the label of that individual falls into our interval would be 95% conditional on that X. But such things are typically impossible in rich feature spaces. And so instead, you might consider marginal guarantees. So your prediction interval would be 95% valid over the entire population. So pairs X, Y. And another famous type of marginal guarantee would be calibration. So basically labels should stay close to what we are predicting. So just a cartoon to keep in mind, maybe imagine a patient stops by the doctor and the doctor looks at the patient's features X and says, okay, here's my diagnosis for you, and here's my confidence interval, L of X, U of X. And the patient might wonder, okay, what kind of confidence interval is that? And the doctor says it's a marginal prediction interval. But this could be problematic. So in particular, say the patient belongs to a very small, like less than 5% subpopulation group, then it's a 95% prediction interval, right? So it can like completely avoid covering such a small subpopulation. And so in our work, we basically give stronger than marginal uncertainty guarantees in the sense that we can be given any arbitrarily large or complex, potentially overlapping family of population groups, and we'll make sure that each of these groups has its own uncertainty guarantee. And additionally, we'll assume basically nothing about the data, so we'll work in an online adversarial setting. And so that covers potential application domains such as time series data, so all sorts of correlates, covariates shifts, label shifts, strategic effects. Compare this to some other important uncertainty quantification frameworks like conformal prediction, where you can often make assumptions like exchangeability, so like only slightly weaker than IID. So our setting, you can imagine being as follows. So we have an adversary, and the adversary gives us at each day from 1 to t a patient and only tells us the features of that patient, but doesn't tell the conditional label distribution of that patient. And we only observe this context, so the features, and then we make one out of 3 possible types of predictions. That's what we consider in this paper. We can predict the mean of that label distribution. We can predict maybe the kth moment, say like variance of that label, or we can predict an 95% confidence interval. And so only once we've committed to such a prediction do we actually observe the realized label for that individual the current round. And so, yeah, as an example, we'll consider mean multi-calibration here very briefly. So as a general introduction, multi-calibration basically says that you should be calibrated on each group in this like potentially large collection of groups, where calibration means that whenever you predict roughly something. So our predictions will be in 0, 1. So if we predict I over n, then on those days, the average true label should also be like I over n. And we can represent it formally by considering these like quantities VGIS. So for each group and for each of these like small buckets that our prediction could fall into, we want our prediction on those rounds where the patient belongs to group G and we predicted roughly I over n to be close to the true label. And we say that the learner is alpha and multi-calibrated if we have these n buckets, and the maximum of the absolute values of these V quantities is small. So that's like our objective here. And notice it's not really smooth, so it's not going to be very easy to handle it. So instead, we'll switch to this softmax surrogate loss. So actually a very close approximation to the maximum of these calibration violations, which is what we really care about. but it's very close it's very close match to this actual objective. So what this gives us is that we can now use like a Taylor looking bound to essentially say the increment in this loss between any two consecutive rounds will only depend on this quantity. So that depends on kind of like the difference between the true label and what we end up predicting in that round. And if all of these increments are small, then we can bound the overall loss at the last round by a telescoping argument. And so let's make the learner greedy. So at each round, the learner will play mu t, the predicted mean, so as to make this increment small only at this round. Doesn't care about any future rounds. And so our framework basically says, okay, let's imagine this interaction as a two-player zero-sum game where the objective that the learner wants to make small and the adversary wants to make large is this bound on the current rounds increment. And so it looks like the learner is handicapped because you have to first choose your prediction and then the adversary says what the true thing was. But actually the minimax theorem says you can flip the order. So we can consider a counterfactual world where we knew what the true label was. Of course, then we can get close to it. So we can be multi-calibrated. And the minimax theorem allows us to actually come up with a so-called minimax strategy, right? That achieves this closeness, even though we are actually going first, not second. And then we can unwrap this and get the bound on the surrogate loss and then get the bound on the multi-calibration loss. Cool. And so we get these types of guarantees like 1 over root t multi-calibration guarantee. And this is optimal even in the distributional world. And so how do we obtain this actually algorithmically? Well, we can. So here's the algorithm. The only takeaway from this slide should be that it's actually a very simple algorithm. So in principle, to compute the minimax optimal strategy each round, we need to kind of solve like a linear program, but we don't need to do that here. So we can like simplify it into just computing some quantities based on our past performance and then predicting sort of either 1 point or actually randomized over just 2 points. So it's also very low randomization, which is good. Okay, and so prediction intervals kind of follow in a very similar fashion. Essentially, we can define quantities that will say, okay, for each individual from like each group, we want our coverage to be close to some 1 minus delta, I think 0.95. And then once again, we can define prediction interval multivalidity by saying that the maximum of the absolute values of these quantities expressing coverage on all these groups are bounded by some alpha. And we know the drill. Now we just switch to softmax loss with respect to these quantities, bound the one-step differences, consider a zero-sum game that has the bounds on these differences as the objective, and let the learner sort of play the minimax strategy. The algorithm here is a bit more complicated. It actually requires us to solve a gigantic linear program, but we simplify it enough to where it becomes polynomial time. We use the ellipsoid algorithm together with some greedy knapsack oracle, to be precise. So in conclusion, this is like a general technique for stronger than marginal uncertainty guarantees in an online setting with the adversarial data. And we can obtain all these guarantees using efficient algorithms, which we provide. And in fact, subsequently, we discovered that this framework can be extended even more to handle convex concave vector losses. And it lets us actually obtain many useful online learning settings beyond even uncertainty estimation. And for future work, it shouldn't be too hard, we think, to extend these results from binary labels, so like 0 to 1, to multi-label, and from prediction intervals to prediction sets, a concept studied widely in conformal prediction theory, let's say. Also, one of our algorithms, as I mentioned, is efficient but not very practical. So maybe can we make it not just polynomial time, but also actually fully functionable? And finally, some experimental evaluation of our algorithms would be good. So do they work better on distributional as opposed to worst case adversarial data? Yeah, that's it. Yeah, thanks very much.
Yeah, thanks a lot, Georgie. Someone has questions, please feel free to ask. Maybe you can stop sharing and then Parikshit can start setting up in the meantime. So yeah, if there are questions, like I said, also please type in the chat. Be fine too. Oh, Mark is here. Yeah, nice to see you, Mark.
Can you hear me, Aditya?
Yes, we can.
And
yeah.
Can you see my slides?
Yes, we can. Yeah. So the next talk is on Omni Predictors. It's more closely related to the previous talk. So Parikshit, the speaker. Yeah, please go ahead.
Yeah. Thanks everyone for coming. This is joint work with many wonderful co-authors: Adam Kalai, Omar Reingold, Vatsal Sharan, and Odi Vida. Now, I'm sure this first slide is entirely explanatory, but since I have 10 minutes, I'll tell you what Omni Predictors are. So we're all familiar with the loss minimization paradigm, which is the dominant paradigm currently in machine learning for training a model. The paradigm goes something like this. You have a loss function L, and then you have a class of models, maybe decision trees or deep neural networks. And then in order to learn, what you do is you try and find the model in this class, which minimizes the expected loss under the target distribution that you care about. So this is a very general paradigm. It's been tremendously successful, but at the same time, it's not everything. We've come to realize that there are certain limitations, especially with regard to desiderata like privacy and fairness. In this talk, we're going to ask a different question. It's again about the limitations of this model. We're going to ask, what do you do if you're not sure upfront what loss function to optimize for, right? So naturally, you might wonder, well, why should we care about this question? And secondly, our whole way of thinking about learning is so tied to loss minimization that it's not even clear that the question that I've framed makes sense, right? For instance, in clustering, we know that the question of finding mean versus finding median can be phrased as optimizing different kinds of loss functions. So now, if I don't even tell you what loss function I care about, what are you expected to do? Okay, so let's talk about why this question is interesting. There might be many situations where upfront, we do not know what the correct loss function to minimize is. Or it might be the case where there are multiple loss functions which are of interest to us, and we really want one model that works for all these loss functions. Or it might be that, the data we have right now, at some point, we'll also learn what the loss function is, but it may not be at the same time as when we have the data to train, right? Like consider something like a medical scenario where the cost of mistakenly prescribing aspirin to someone is very different from the cost of saying do some kind of invasive surgery and getting that wrong, right? So when you have a situation like this, the loss minimization paradigm, it doesn't necessarily give you a very satisfactory answer, even when the losses in question are all nice and convex. You could have a different optimal for each loss. And in general, to get provable guarantees, at least, you need to retrain from scratch every time. Now, of course, using things like transfer learning, you could argue, well, no, it's not really from scratch, but there's no provable guarantee saying, okay, you optimize for this thing, then you're halfway or more there to optimizing for some other loss, which might be very different. Because as this picture, which I'm not going to have time to explain, tells you, there's the geometry of the space could be such that different losses are optimized at very different points in the space. Right? This is a real problem. There's a bunch of heuristics out there which will minimize for certain losses like L2 squared loss or some other truthful loss function. And then they just pretend like these are the ground truth probabilities and you hope for the best, right? The question here is whether we can do something better. Okay. So it sounds like a problem which is crying out for a definition. And that is the main conceptual contribution of this work, is this notion of an omni predictor, which we think of as one predictor to rule them all. So the setup here is that you have a family of loss functions. Loss functions, they take a 0-1 label, which is the true outcome. They take a prediction, which let's say it's a real value, and then they assign a loss to you. If the label is 0, you predict this, here's your loss. If it's 1 and you predict this, there's your loss, right? And then there is a hypothesis class C. Given this setup, an LC omni predictor, it's just a function which takes each point and predicts probabilities in 0, 1, such that for any loss in this class, there exists a simple post-processing function. This post-processing function doesn't look at the data, which could be very high dimensional. It only looks at the prediction that you make and gives you a real value. The guarantee we have is that for any loss in the class, for any loss in L, the expected loss we suffer by post-processing F is less than the expected loss compared to anything in C. And this includes the best hypothesis, which is probably optimized to this particular loss function. Okay? So this is a lot to unpack. We want to learn this predictor once and for all, which just predicts probabilities. Just by post-processing these probabilities in a way that's specific to the loss, we can do better than anything in C. This is the goal that we've set. Okay. Now, why is this even possible? Why is this not a null notion? It's because if you had something called the Bayes optimal predictor, which just predicts the conditional value of the label given a point X, it is folklore and easy to show that this is an Omni predictor, no matter what L is, no matter what C is. What this means is that if you know the probabilities, the optimal probabilities, the right probabilities of the label for every point, you can always make predictions which are optimal, not just an expectation, but even point-wise optimal, right? And this post-processing is the easy part. The hard part is that computing this Bayes optimal, it's information theoretically and computationally impossible. So the question really is whether we can compute this notion of Omni predictors efficiently for meaningful choices of L and C. So this answer, it requires a bit of digression into the area of multi-group fairness, specifically this notion of multi-calibration that Georgi talked about. This was introduced by Hebert, Johnson et al. Now upfront, I should say that this is a notion of group fairness. There is no loss function in the definition, right? Calibration is a well-known notion. A predictor is calibrated if the expected label conditioned on the prediction is the prediction itself. Multi-calibration just asks for calibration conditioned on every subpopulation from a large class C that you care about, right? So the C in their work, it's meant to capture subpopulations that we wish to protect. In our work, it's a hypothesis class. So we extend this definition in a way that allows you to think about real valued functions C and so on. And this notion, let's just say that they Hebert, Johnson et al. Showed that it's efficiently computable given a certain learning primitive for the class C. So this brings us to our main theorem, which says that if the predictor F is multi-calibrated for the class C, then it is an LC omni predictor, where L is the class of all convex Lipschitz loss functions. Okay. So you just take the outcome of this predictor, you post-process it, you're competitive with any hypothesis from the class C. The post-processing depends on the loss, but nothing else does. This means you can really train all at, the training can be done independent of the loss. All you have to know is that I'm interested in a convex loss function. You can train when the loss is revealed to you, you can post-process the predictions. And the post-processing here is exactly the same as what you do if you knew the Bayes optimal predictor. So it's very simple. You need the class L of loss functions to be convex. This Lipschitzness condition, we can relax it a little. We don't need it to be Lipschitz everywhere. But this theorem, it includes LP losses, logistic loss, exponential loss. Basically, every loss function that I am aware of is covered by this theorem. Right? So now, why is this interesting? Well, this has this good karma interpretation. Multi-calibration is a fairness notion. The authors swear to me that they weren't thinking about loss minimization when they came up with this. Yet it gives you this incredibly strong loss minimization guarantee that we don't know how to get otherwise. Right? And one interesting contribution here is a new view of what multi-calibration should mean. I'll just tell you what this view is and then wind up. Right? We think of multi-calibration as the partition of the input space which satisfies the following pseudo-randomness property. Within each partition, for everything in C, the expectation of Cx times Y is the product of the expectations. So it's almost as though C and Y are independent condition on a partition. Right? And now from this, getting a predictor is very easy. Within each partition, you just predict the expected label. So the intuition here is that the real process which is going on it looks as though within each partition, points are just flipping coins with different biases and deciding their label, right? This is just intuition, but there is a way to formalize this using the outcome indistinguishability framework of Dwark et al. So in summary, what we are proving here is that multi-calibration gives us a very strong loss minimization guarantee. This relies on a new view of multi-calibration itself as a partition, which I think is independently interesting. It gives us a way to define learning without a loss function, more in the sense of a structure versus randomness decomposition. There's a lot of rich connections to work in agnostic learning, which was done about 15 years ago, but it turns out to connect very closely to this notion of multi-calibration. It points out some interesting contrasts with multi-accuracy. It's a notion which I haven't defined, so I won't be able to tell you more about this. In terms of future directions, I think the most pressing future direction is that multi-calibration is this really nice notion from a fairness and now also from an optimization viewpoint. The sample complexity to achieve it is really high. It gets worse when you're doing multi-class classification, where it's exponential in the number of classes that you care about. There are some works which attempt to remedy this, and they come up with relaxed notions which don't have such high sample complexity. But I think this is still a very interesting direction for work. So I'll stop right there. Thank you very much.
Well, thanks a lot, Parikshit. It was a great talk. And any questions from the audience? Any of the other speakers? So yeah, so I think Paul is here. So can you share your screen? Oh, okay, yeah. All right, so I think the last speaker of the session is Paul Valiant. He'll talk about optimal sub-Gaussian mean estimation, very high dimensions. So there is one question for Parikshit. We can come to it right after, or maybe you're typing an answer, so that's great. Okay. All right, so Paul, go ahead.
Okay, great. Thank you. So, sorry, can you hear me? Okay. Optimal sub-Gaussian mean estimation in very high dimensions. So I'm Paul Valiant. This is joint work with Berkeley. So today I'm going to tell you about two problems. The first one is the classic problem of statistics of mean estimation. Given samples from today, a very high dimensional distribution, we want to estimate its mean as well as is possible given our data. More on this in a moment. The second problem which I want to tell you about, which at first glance seems rather different, is that of coming up with good tail bounds. So here, suppose you have the sum of independent bounded random vectors with some total covariance. How can you come up with a high probability bound on the distance, L2 distance of the sum from its mean? In other words, we're seeking a vector analog of the Bernstein inequality. So a guiding idea here is that in some sense, the most interesting thing to me about high dimensional Gaussians is that as the dimension increases, these Gaussians start looking more and more like a spherical shell. So to give you an illustration of this, so if you look at the distribution of the length of a Gaussian, standard Gaussian random variable in D dimensions, normalized by 1 over root D, in one dimension, the distribution of length doesn't look like much, it's just half the Gaussian. But as the dimension increases, you can see that the length starts adhering more and more tightly to a spherical shell, in this case at radius 1. And the challenge is to try to capture this with a tail bound. Previous tail bounds, in some sense, don't capture this spherical shell behavior very well. And one way of saying this is that spherical, previous tail bounds, in some sense, apply for all dimensions without improving with the dimension. So because they're too uniform with respect to the dimension, they fail to adhere tighter and tighter to a sphere as the dimension increases. So this is the second challenge that we're going to talk about today. Okay, so to go back to the main mean estimation problem. So again, this is one of the most important problems in statistics. Given data, how do you estimate the mean of the underlying distribution? This also shows up as a subroutine of various computational processes. But it's also one of the most important primitives of real-world data analysis. So supposing you've got some expensive experiment that's producing some data. I'll illustrate it just in one dimension. So if you have collected these 8 data points, how do you estimate the mean of the underlying process? Well, returning the sample mean is a very sensible thing to do. And if your distribution is a Gaussian or something well-behaved, the sample mean behaves extremely well. But what if you continue collecting data and you get maybe some sample point extremely far to the right? What do you do? Do you take it seriously? Do you throw it out? What if you get 2 data points? So how do we view this algorithmically? So if 2 out of our 10 data points are outliers, well, this is in some sense compatible with a ground truth where the expected number of outliers we should have seen is maybe as low as 1/10 or as high as 4/10. And algorithmically, in some sense, what we're trying to capture is we're trying to understand what are the most extreme distributions that could have led to the observed data. And then we want to return an estimate that's accurate enough to be compatible with all such distributions that could have led to our observed data. However, if we see 2 out of 10 outliers, maybe we just got really unlucky. Maybe we should have seen 0.0001 outliers and we just got unlucky. So, it's 1 in a million unlikely to see 2 out of 10 outliers if the true probability is this. But, whether our algorithm is allowed to throw out this scenario or whether our algorithm must take it seriously depends on the desired confidence of our answer. So if we want our algorithm to be correct, except with error 10 to minus 6, then we do need to take this possibility seriously. So, okay, the goal of mean estimation, given samples from some distribution, we want to estimate its mean to within distance epsilon with probability 1 minus delta. Namely, we want to understand the optimal trade-off between these 3 parameters, the number of samples n, the accuracy epsilon, and the confidence delta. Today, I'm going to focus on the high-dimensional case, where dimensionality we'll look at in terms of what's called the effective dimension, very standard quantity, which is the ratio of the trace of the covariance to the maximal variance in any direction. The effective dimension behaves exactly as you would like. So for distributions with a spherical covariance, it just counts the number of dimensions of the sphere. Some distributions have covariance that looks more like a pancake, and here the effective dimension essentially counts the number of big dimensions of the pancake. And exactly the regime of effective dimension that our result applies to is here. So, okay, how do we get started on this problem? Well, the ideal case for mean estimation is when the distribution is extremely well behaved, like a Gaussian. And for a Gaussian, the provably optimal thing to do is to return the sample mean. So it's good to ask, how well does this work? So given a Gaussian of some covariance, how well does the sample mean work at estimating the variance? Sorry, at actually returning the true mean. So as we've described, Gaussians have this spherical shell behavior in high dimensions, where the error of this estimate is going to be extremely close, 1 plus little o 1 times this radius of this spherical shell, where the radius depends on the trace of the covariance. So Gaussians, the error for Gaussian mean estimation behaves like a spherical shell. The question is, what can we do in general? So we're going to have an unknown distribution with unknown covariance, and we need to design an algorithm. We want to design an algorithm that tries to emulate this. And the main result is that we will do this, provided n is sufficiently large. So we're going to come up with an algorithm that for any distribution is going to emulate the spherical shell performance of Gaussians. Okay, so there's lots of prior work on mean estimation, including a lot of recent work on mean estimation, including a lot of work on even the one-dimensional case. So my co-author Jasper Lee is presenting what we hope is the culmination of this line of work next week at Fox. But so in the high-dimensional case, this is a brief description of some recent results. And I'm using this slide just to point out that this problem is daunting. So it took until surprisingly recently, 2019, to get any kind of algorithm, even an exponential time algorithm that is constant factor sample optimal. So it's taken a lot of work to improve the computational complexity. And even from a perspective of the sample complexity, if you look under the hood, some of these factors are as big as 1 trillion. By contrast, today I'm going to tell you about a linear time algorithm, which is 1 plus little of 1 optimal in terms of sample complexity. And it's extremely simple, as I trust you'll see, but at the cost that the algorithm only works in very high dimensions. So, okay, as motivation here, the good performance of the sample mean for the Gaussian case comes from the fact that in high dimensions, Gaussians adhere to a spherical shell. So it's natural to ask, can we extend these spherical shell tailbounds beyond Gaussian distributions? So we're going to start with the standard one-dimensional Bernstein bound, which describes if you have sums of independent random variables that are bounded. The Bernstein bound in some sense combines two kinds of information. It combines information about the variance of these random variables with a bound R on the support sides of these random variables. And the denominator here has interaction between these two terms, showing essentially how Gaussian bands gracefully degrade in the presence of outliers at a radius of R. So the new tail bound that we're introducing generalizes this, we think, very naturally to high dimensions. So we have sums of independent random vectors, each bounded by some radius R. And then our bound is on the distance of the sum compared to the radius of the spherical shell. So what's the probability that the distance of the sum is t more than the radius of the spherical shell? And the probability that we find is extremely similar to the Bernstein bound. A very natural generalization, we think, and it's not hard to check that it has this spherical shell behavior, namely, as the effective dimension increases, this band adheres more and more tightly to the spherical shell. So, okay, the claim in this talk is that this tail bound is the crucial ingredient to coming up with a simple algorithm. So let me tell you about that now. So how do we use this tool to give us an algorithm for mean estimation? So this tail bound applies for bounded distributions. How do we take a general distribution and get a bounded distribution from it? Well, trivially, we can pick some ball of radius R, and conditioned on samples being in this ball, then the samples come from a bounded conditional distribution, so we can apply the theorem. There's some delicacy to choosing the right R, but given this, the algorithm is extremely simple. So this is our final algorithm, which is the main result of the paper. Step one, roughly estimate the mean with classical coordinate-wise median of means algorithm. Step two, compute S in terms of the desired confidence level delta. Throw out the S farthest samples from our center of our ball that we've chosen, and return the mean of what remains. This is our algorithm. It's linear time, and this is the main result. So I just want to end with a brief comment contrasting this 1 plus little o of 1 factor tight algorithm with this tail bound. The tail bound we think is useful, it's new, but it's not quite 1 plus little o of 1 tight. So to draw a diagram of this, consider the probability distribution of the mean estimation error. So the ground truth is going to adhere very tightly to some spherical shell. And supposing instead we have a tail bound that bounds things less tightly. Is this good enough? Well, recall that the overall goal is to understand, for some given confidence delta, what the delta probability tail of the mean estimation error is. And the point is that even though the red and the blue curves might be very different in the vertical direction, in the horizontal direction, the ratio is going to be 1 plus little o of 1, because both of them, both the red and the blue, adhere extremely tightly to the spherical shell. And this is what gives us our 1 plus little o of 1 algorithmic performance, even when our tail band is not 1 plus little o of 1 tight in the probabilistic sense, namely in the vertical axis here. So in summary, this notion that Gaussians behave like spherical shells in high dimensions, this is the intuition behind this paper. And the fact that we get a spherical shell tail bound is the big win that gives us the rest of the paper. Given this tail bound, our algorithm is very simple. It works for simple, robust reasons. And we hope that the simple and robust implications of this tail bound mean that the tail bound might be useful much more broadly. Okay, thank you.
So, Paul, so yeah, any questions? I think one question in the. Okay, this is so yeah, so I had one quick question. Like, do you know if this sort of thing does not work in lower dimensions? Do you really need the high dimensionality?
Okay, yeah. Great question. So one thing which I skipped over. So this algorithm throws out the square of the log of the robustness samples. So in the optimal 1D algorithm that Jasper's going to present in Fox next week, we need to throw out just a single log instead of a log squared number of samples. So this discrepancy, in some sense, shows why this algorithm can't just transparently extend to low dimensions. So we don't think this is a low-dimensional algorithm. We think the full problem of coming up with tight analysis for all dimensions will involve significantly more work. But the point is that the spherical shell behavior gives a very easy analysis for a particular regime, namely the high-dimensional regime.
That's very cool. So any other questions? I think we are almost at the end of our time, but I think we have the room. So if there are questions, feel free to ask. I think there's one in the chat, Paul. I don't know if you can see. Uri asks, do you expect a smooth transition in the power of log 1 over delta as the dimension grows?
Yeah, okay, that's an interesting question. So the algorithm here and the algorithm in one dimension in Fox next week, both sort of can be represented as just throw out a certain number of samples that are far away. And this isn't the way that most algorithms in this area look. So most algorithms do something much more complicated. So the right answer, the optimal answer, might involve something rather more nuanced that maybe does rather different things in different directions. So again, in a very high dimensional space, there's many different directions, and you might want to treat samples that are outliers in one direction differently from samples that are outliers in a different direction. So I think that might be where the nuance lies instead of just picking exactly the right number. So I think the final algorithm will actually be more complicated than this. But the reason this paper, I think, is fits in ITCS is because the algorithm is simple.
Yeah. All right. Yeah. So let's thank all the speakers. This was a great session. So thanks a lot for coming by. I know that online conferences can be a little straining. So thanks to the audience also for making it. So yeah, thanks a lot. Yeah.